Section 3.10, the last section of Unit 3 or Chapter 3, whatever they're calling it in this book, is on systems of equations. And when I think about a system, I think about many pieces coming together to work as one thing or to do one thing together. And so here we have these equations and they're going to work together to solve a problem. So we're going to have to set them up. We're going to have to be able to find solutions of them. And we're going to do that using graphs, tables, and substitution. And we're going to need to recognize when something is not a solution. Sometimes that is very important, actually, to recognize what won't work in order to come to an understanding of what will. And then we're going to, of course, interpret solutions. A few recalls. The additive property of equality. Okay, remember that said if you start with something that's equal, then, and if you add or subtract the same amount from both sides, you will end up with something else that's equal. For instance, if I take away 2 from both sides, I still know that 5 equals 5. And let's see, we also had the multiplicative property of equals. And that said, if I start with 2 things that are known to be equal, so 2 equal quantities, and I scale them up or down, I just have to do it to the same on both sides for it to maintain equality. I don't know, let's scale down by -2. So let's take an opposite and half of each one of these. Still equals. And I have another recall, and because we're talking about solutions, so we're talking about equations and equals, and we're also going to talk about solutions. So remember that a solution to an equation makes it truly equals. Yeah? Okay. Example 1, using a graph and a table. Create a table of values for the equation y equals 5x minus 3. Okay, that's not even part, but it's something I have to do, apparently, to do the parts. So let's start with that. Create a table for this. Okay, how about 0, 1, 2, 3? Squeeze it in there. So when x is 0, 5 zeros is 0, take away 3 is -3. When x is 1, 5 one time is 5, 5 minus 3 is 2. When x is 2, 5 two times is 10, 10 take away 3 is 7. When x is 5 3 times, or 3 5 times, however you want to say it, is 15. 15 take away 3 is 12. Okay, I made a table of values for this equation. Use the table to solve the equation 5x minus 3 equals 12. Okay, well, this, right, is really saying y is equal to 12, because up here we said that y is equal to 5x minus 3, so that must mean 5x minus 3 is equal to y. So I can replace this with a y, go back to my table and see, oh look, right here, y is equal to 12, like this is reading, and when that happens, x is equal to 3. Okay, so here is our solution to when this will happen, when 5x minus 3 will equal 12. Check that this is really a solution. oh, in order to check if something is a solution, I remember that we put it in and we make sure it is really equals. So 5 by 3 minus 3 is equal to 15 minus 3 is equal to 12. Good to go. Because we wanted to make sure that when we put in 3 as the quantity for x, it would equal 12. And voila, it did. Use the table to solve the equation 5x minus 3 is equal to negative 13. So again, we're looking at this and we're thinking to ourselves, well, that's the same as y, because 5x minus 3 is equal to y. So 5x minus 3 is equal to y. But I do not see negative 13 in my list of y values. So I'm actually going to have to extend my table of values. Let's go maybe over here. And we're going to go backwards. So maybe negative 1, negative 2, negative 3, negative 4. Hopefully it'll be in there somewhere. Okay. I did notice that this is a linear equation and our pattern was plus 5, plus 5, plus 5. So I'm actually going to use that to make this quicker to fill in. I'm going to go how much plus 5 would give me negative 3, and that's negative 8. So notice if I'm going forwards it's plus 5, but now I'm deducting 5 in order to undo that. So let's see, minus 5 would be negative 13, minus 5 would be negative. Sorry. Negative 18. I was just seeing more and more patterns as we go through this problem, yeah? Minus 5 again would be negative 23. Okay. Did we, oh, I guess I didn't have to go that far. I just got caught up in the pattern and pattern recognition. I just noticed this alternating 8-3 business with the 10s. But anyway, so when is y equal to negative 13? Right here. When x is equal to negative 2. Okay, so check that that is really a solution. Okay, so here we go. We don't need this. 5, and we're saying the quantity for x should be negative 2. And minus 3. 5 sets of negative 2. Yeah, that's negative 10. And then take away 3, that's negative 13. And yes, 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 we did it. Sweet. Okay, let's do this again, but for a new, oh no, not the same. So let's create a table of values for this equation. Oh, okay, I see. I see that there's a half here, and I am going to do this. I'm actually going to create 2 tables for this because I know what halves do. So I'm going to go like this, and then I'm going to make another one. So half of 0 is 0. That plus 1 is 1. A half of 1 is a half. Take its opposite, so it'll be a negative a half, plus 1. Well, 1 take away a half is a half. 2, half of 2 is 1. A negative 1 plus 1, so down 1, up 1, zeroed out. And here's what I'm noticing. I'm noticing when I put in even numbers, half of an even is a whole number. So I kind of like the idea of going even style. So here's what I mean. Okay, half of 4 is 2. Negative 2 plus 1 is you're down 1. Half of 6 is 3. Negative 3 plus 1, you're down 2. And I can see the pattern here. I bet this is negative 3. Half of 8 is 4. Negative 4 plus 1, down 3. Okay, so I see a pattern. And it's nice to take half of things that are divisible by 2. Graph the equation. Ooh, graph this equation by hand. Okay, so it looks like I'm going to be plotting some points. And I don't think I really need to change my scale, so that's nice. Because I think all of, wait a minute. 1, 2, 3, 4, 5, 6, 7. Oh, I'm going to have to go a little bit out, but that's all right. You know what? I'm going to move my axis. What are you going to do? How big do my y values get? Negatives and... Okay. So this is my y, my response, and here's my x. So far, we haven't had any word problems. What is going on with this section? Okay. Right. Here we go. 0, 1. Done. Oh, and all of these are counting by 1, so I should mark that somehow. 1, 2, 3, 4, 5, 6, 7. We'll mark this as 8 so that we know. And 1, 2, 3, 4, 5, 6. I'll just mark this as 6 so that we know this scale is counting by 1s and this scale is counting by 1s. Okay. 1 and a half. 1 and 1/2. Got it. 2, 0. 4. So 1, 2, 3, 4, -1. 4, 5, 6, -2. 8, -3. 1, 2, 3. And then I connect my dots. Okay, I grab my handy ruler, my straight edge, and I try to make this line up as best as I can. Did I just say bestest? What are you going to do? Okay. Graph the equation by hand. Done. And use the graph to solve the equation -1/2 x plus 1 equals 3. Okay, so I noticed that y is equal to that. So first off, this side is the same as y. So -1/2 x plus 1, that is exactly what we see here equaling y. So this says that the y is equal to 3. Okay, that's this vertical thing. So we go 1, 2, 3, and then we go over 1, 2, 3. I think it's -4. So just to kind of map out what I just did, right? Like this, is that -4? 1, 2, 3, 4. Okay, so based on this graph, I'm predicting that when y is 3, x is -4. Check the answer here. Sure, I will, for sure. So -1/2 by -4 plus 1. Well, half of $4 in debt is $2 in debt. The opposite of that is not in debt. So we got +2 plus 1, which equals 3. Yay! Got it. Now use the graph to solve the equation -1/2 x plus 1, which again we know is y, is equal to -1. Okay, so now we're looking at the graph to where y equals -1. And I'm going over here to the graph of the line, and then up here to see what the x is. 1, 2, 3, 4. My guess is that this happens. Oh, I better circle the solution so that we don't get mixed up here. My guess is that the solution to this equation is that it's truly equal only when x is 4. I also want to mention, we're going to check that answer. You know what, before I do another mention, let's go ahead and check that. So -1/2 times 4 plus 1. Half of 4 is 2. The opposite of positive 2 is negative 2. Negative 2 plus 1 is still in debt by 1. So yes, that did make this truly equals. I also want to mention, if I go up here, right there, I see that it's in my chart, right? So when x equals 4, y equals negative 1. So I could use the graph to find this answer, and I also could have used the table of values. They're all tied together, yes? Okay, so let's make some remarks about this stuff. A solution to an equation in one variable. Okay, and when I say something like this, I mean this is an equation and it only has one variable in it. So an equation, one variable, what's the solution, right? And this is the value of the one variable that makes the statement actually equal. So okay, so it is the value of that one variable that makes the statement or the equation actually equals. And you should be able to check it. And it would be easy to find a lot of non-solutions, but sometimes we like to have the real solution. But let's take, so that was in one variable. And now a solution to an equation in two variables. So when I look at this, I think, well, here's an equation and it has two variables. It has an x and it has a y, right? So is the values of both variables. Okay, so here, the solution to an equation in two variables are values of both variables that make the equation actually equal. And so notice how in this last example here, we had an equation and we found its solution. And if we had had this equation in two variables, right, x's and y's, we would have said, when y equals negative 1, the x value is 4. Or when x is equal to 4, the y value is negative 1. We would use both. So I want to mention that these can be checked as well. So we checked these solutions in one variable up here, but these are checked by putting x equal whatever number and y equals whatever number as a coordinate pair into the equation to make sure it works. Simultaneously. Okay, so you could check it just like you check these. You would just have to put in both of those at the same time and make sure it still isn't equal. Okay, and I also want to make a quick mention. I hope, yeah, okay. I put some space down here because a lot of times textbooks would say a solution to an equation in two variables is an ordered pair or a coordinate pair. And that's absolutely true. X equals some number and y equals some number is a pair that coordinates together. So we absolutely can write these as a coordinate pair, right? We could either say when y is this, x is that, or we could say here is the pairing of them together as a solution. Okay, a set of equations. The price of a product A was $20 in 2005 and has been increasing at a constant rate of $5 per year. Got it. The price of product B was $50 in 2005 and has been decreasing at a constant rate of $1 per year. Write an equation describing the price of product A after T years since 2005. Okay, got it. So they gave us our variables. Well, maybe I'll call it PA. I'll just call it A. So product A, let's see, what is the initial? The initial was 20. So just to have these written down. Initial equals 20. Constant change equals increasing rate of $5 per year. Got it. Initial of 20, increasing $5, oopsie, T. Okay, good. I was like, did I forget the right variable? $20, increase of $5 for each year, or 5 times, or, however many years goes up. Now do the same thing for product B. Okay, product B has an initial at $50 and a constant change or slope of decreasing at $1. Decreasing by 1. So product B is equal to its initial take away 1 for each year. So take away 1 T times for each year. Write these two equations as a system. So these two things are happening simultaneously. You've got two products on the market and they're behaving differently, but they're both yours. So here they are as a system working together. Yeah? Okay, it looks like the word it, so I'm going to turn that into a fancy one. Which is the goal of finding when prices will be the same and what price that will be. So because this is the price of product A and this is the price of product B, and if they're working together, the question is when will they be the same price? Okay. Use tables of values in order to find when the prices of the products will be the same. Okay. Well, for product A, so we got T for time and years, and we have the price of product A. Maybe I should have called these prices, like PA, price of, whatever. Anyway, let's see what happens after 4 years. So it starts at $20. After a year, it's increasing by 5. So 25, 30, 35, 40, and so on and so forth. Price of product B, so we got T years. Price of product B, let's go 0, 1, 2, 3, 4 years later, or after 4 years. And it starts at $50 and it's going down. So the constant change is going down by 1. So 49, 48, 47, 46. Ooh, I think we might have a matching at t equals 5. I've run out of space here. Let me write this down. When t equals 5, product A price is $45. That would have been, right, the next increment of 5. And here, when t equals 5, the price of B equals $45. Ah, use the table of value in order to find when the prices of the products will be the same. Oh, when? Let's see, go back to this. In 2005, that's when this whole thing started, and this is 5 years later. So find when? Ah, in 2010. So in 2010, the price of both is $45 each. Nice. Okay. Use a graph in order to find when the prices of the products will be the same. Oh, I need my graphing calculator. Here it is. It's so handy. Okay, let's zoom in. All right. I'm going to go to y equals, but I've been using this. I think that's rubles conversion. I'm going to clear that. I also plotted a scatter plot, so I have to go to second. So second stat plot. I'm going to hit enter, and I'm going to arrow over right here to off and hit enter. Now I'm going to go back to y equals. So the scatter plot is now off, and I'm ready to input my product A equation, 20 plus 5x instead of t, of course. And my second equation is 50 minus 1x. Hit enter. And now I'm going to go ahead and I'm going to go to zoom, because remember it was on that scatter plot, and I'm going to go down to 6 and hit enter. Here we go. Okay, so we definitely have to zoom out because one of them is showing up but not in the vicinity that we need it to be. So I'm going to have to go zoom out, enter. And I think I'm going to zoom out over here. I don't know, something of the sort. Oh, well, we're close. It's up here somewhere, yes? So I'm going to have to do it again. I'm going to go zoom out, enter, and I kind of want to be a little bit closer to up here, so I'm going to go there. All right, so now that we have both lines intersecting, we can find where they meet or when they're both the same. So here we go. I'm going to go second, calculate, and notice here's number 5 where they intersect. We've done this before. Hit enter. First curve, yes. Second curve is the red one. Guess, sure. Ah, and there is our intersection. And so notice it says x equals 5, and when x equals 5, y is 45. Okay, so use our graph in order to find out when the prices of the products will be the same. So just to give a rough image of what just happened, right? We had one line going like this. We had one line going a little bit like that. And right here is where they met. And this said, it didn't show this, but when x equals 5, y equals 45 is what it said. So why am I using that one? it gave us this for the intersection. Use the graph in order to find when the price of the products will be the same. And notice we get the same exact answer. In 2010, the price of both is $45. So the price of product A, $45. The price of product B, $45. And that's when x equals 5, which is 5 years after 2005. Write the solution as an ordered pair, then write a sentence that describes the meaning. Oh, well, lucky us, we can write 5, 45. And just remember that 5 years, that's 5 years after 2005. And that is the price of each one of the products. So, same. In 2010, which is 5 years after 2005, product A was $45, and so was product B. Yeah? Okay, so there is the solution in the context of this actual scenario. All right, let's make a few remarks before we talk about solutions and whatnot. All right, first remark. A system of equations is any group of equations working together to solve a problem, okay? So a system really does mean we need to work all of these things together to find our answer. A system of equations is any group of equations. So it doesn't have to just be two, it could be more than that, because that's more constraints on one situation, or more than one data point in order to come to a solution to a problem. A system of equations is any group of equations working together to solve a problem. Okay, and then next, my next remark, or something that's remarkable about systems, is a solution to a system can be found by making a table and seeing where they match. We actually just did that. So, a system of equations can be solved by making a table and seeing where they match. Yeah? Okay. And when I say match, I mean both X and Y, right? I'm going to squeeze that in here. No, I'm not. Okay. And another way, so we did this using a table, but we also looked at the graph and saw where they intersected. So, a system's solution can also be found by graphing and finding where they intersect. Finding where the lines intersect. I'll write it here. Remember that that's both an X and a Y, and they have to correspond to each other. So that when I think about a solution to a set of equations in two variables. Again, so we mentioned this once, but I'm going to mention it again because now it's a system of equations. So it's not just one equation, but now we have a set of equations, right? But just two variables. And I said set because it could be more than one equation or more than two equations, but the solution is two values, x and y. So the solution is two values, both x and y must be known. Okay, and these make both equations actually true. Or actually equal. Yeah? So you can't just make one equation true. You got to make both equations actually true simultaneously. In the next video, we will look at a new way. So we did a table and a graph to solve a system of equations, and then we're going to look at more and another technique.